Hello, everyone, and thank you for attending today's webinar, Practical Quantitative Analysis. Before we begin, as usual, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget at the bottom and submit your question. We'll try to answer as many of the questions we get as possible during the webinar. But if a fuller answer is needed or we run out of time, you'll get an answer later via email. We do capture all the questions we get. A copy of today's slide deck and some links to additional material are available in the resource list widget that looks like a green folder. You can expand your slide area by clicking on the maximize icon on the top right or by dragging the bottom right-hand corner of this slide area. If you have any technical difficulty, please click on the Help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately half a day after we finish it, and that can be accessed using the same audience link that was sent to you earlier. Now I would like to introduce Tara Niles and Dr. Jens Raffelsson, who are our presenters for today's webinar. Tara is the EDAX Global Applications Manager. She works with EDS, EDSD, and WDS techniques. She started her career in microanalysis primarily with SEM-EDS-based techniques, and over the course of her 21 years with EDAX, has added the additional capabilities into her analytical approaches. With a strong understanding of core technologies, Tara takes the advanced techniques in novel directions externally with customers and internally within various EDAX groups. Dr. Jens Raffelsson joined EDAX in 2014 as an applications engineer specializing in EDS. He has a strong background in electron microscopy and has trained numerous students and clients in SEM and EDS theory and practice. His experience includes several years as the technical supervisor of the cleanroom facilities at Aalborg University, Denmark, where he applied a variety of techniques, including SEM, FIB, CVD, PVD, PES, AFM, laser spectroscopy, and optical, electron, and ion beam lithography. So now with that, over to Jens for the beginning of the presentation.
Thank you, Sue, for the introductions, and good morning, good afternoon, good evening to everybody joining us. We will start today's presentation or webinar with just a few of the very basics. So first, a little bit about X-rays, very brief, and a little bit about how quantification works, since we're going to be talking about the accuracy and precision and how to get things better. This all comes down to statistics and counts in the spectrum, basically, so we'll show that in a few slides. And we will also talk a little bit about pileup correction. Then Tara will go through and show some examples where we vary the process times and see what performance we can get out of it, collection time, rates, and speeds, and how this all works at low count rates, since you can't always run high count rates for every single sample. And we'll finish off with one of the more complicated examples, which is a Galena sample, followed by a summary of today's webinar. So let's start with the basics, X-rays. The emission of X-rays inside the SEM is whenever we knock out a core shell electron from a given nuclei, and the outer shells drop down. So there's a probability of emitting an X-ray, and there's a probability of that happening in the first place, depending on the current number of electrons we have going down through the microscope. So it is a random process that occurs due to the inelastic scattering of the electrons that we send down. And the X-rays will be emitted in all directions inside the sample. Fraction of those will happen to be emitted in the direction of the EDS detector that we have mounted inside the microscope. And in the EDS detector, we capture the X-ray and then measure the energy of each individual X-ray. And this happens one X-ray at a time. So to build up the spectrum, we take the X-ray energy that we measured and put one count into our spectrum. And then we end up with a spectrum where the energy of the X-rays will be the x-axis, and the number of X-rays coming in at that energy will be the y-axis. Once we have a spectrum built up, we then compare to our known values of the X-ray transitions for the different elements. So these are very well documented, and we can go through this databases or other resources to figure out exactly where are the different transitions and what's the transition probability. So here on the right-hand side, I show the emissions lines for carbon and oxygen, where we pretty much only see the K alphas, and then we have the silicon, where we have a K alpha and a very small K beta. So once we know what those emission lines are and can match it up to our spectrum, we can identify the peaks in our spectrum. So in this case, our sample is a silicon and oxygen-rich sample with some carbon, and this is a carbon-coated quartz sample. That's the detection and identification. For the quantification, we need to start modeling everything. First thing we do is apply a background model. So this is due to general slowing down of the electrons inside the sample, so they are emitting continuum X-rays, not characteristic peak X-rays, and we call that Raumstrahlung or background. So we apply a model. That's the slight blue line you can see down the bottom of the screen. If we zoom in, we can see it's a little more complicated than that. The background model is a continuum approach, but we also need to take into account all the absorption of the different elements inside the sample. Here we can see there's a sharp jump in the background from the silicon absorption line, and we also have the oxygen and carbon from within the sample, and this is a silicon nitride window, so those absorption lines play a role as well. And then the detector efficiency, of course. Once we've modeled the background, then we can separate out which counts in the spectrum come from background and which counts come from the characteristic peaks. So really figuring out how many X-rays did we get from silicon, how many did we get from oxygen. We integrate up over the width of the peak for the different elements, and then we compare that number of integrated counts to the number of counts we would expect if we had a pure element standard in there. So if we had a pure silicon sample under the exact same conditions, how many counts would we get? And then we scale that relative to the counts we got in this sample. So we call that number the K ratio. And that's the first guess at the concentration of the given element. So simply comparing the counts in the peak to the counts we would expect if we had a pure element sample in there. The problem is that we very rarely have a pure element sample, so we need to apply some correction factors to compensate from this deviation from a pure element standard. And these correction factors are generally called CAF. C is an atomic number factor correction, A is an absorption correction, and F is a fluorescence correction. So once we click the quantification button, we get a series of results here. That this is a quartz sample and it's carbon coated, so I applied a carbon coating correction, which means we don't quantify the carbon per se in the sample. We apply that as an additional layer on top. But what we get here is the net intensity, which is the background subtracted integrate number of counts in the peak, and we then scale it by the acquisition lifetime. So it's number of counts in the peak divided by the acquisition time, the intensity of the peak. Then we have the K ratio, which is the ratio relative to what we would get if we had a pure element standard in there. So we can see here we get about 40% of the counts for silicon as we would get if we had the pure silicon sample in there. So we get the first number, of course, from the integrated counts in the spectrum, and the second number, the pure element, is a first principle calculation. So this is pure standard less quantification we're doing right now. Then we have the atomic number correction. This is primarily to compensate for backscatter yield and changes in stopping power. A pure carbon sample would have much less stopping power than, say, an iron sample. Then we have the absorption correction, takes into account what's the probability of a given X-ray escaping from the sample given the mix of elements that's in there. So the lighter an element is, the lower energy the X-ray line has, the higher probability of absorption. And the last correction factor is the fluorescence correction. This is to separate out the X-rays generated from the electrons of the SEM and those generated from the fluorescence from X-rays from heavy elements or the background themselves. All those correction factors are applied, and we also get an estimate of the expected precision of the quantification numbers. So this is the expected variation of the quant numbers in percent. And we output the calculated weight and atomic percent based on the K ratio and correction factors that we measured and applied. The important part to remember is this. The quantification model applies a series of assumptions, and that means the sample has to meet the following requirements. It has to be homogeneous, it has to be flat, and it has to be infinitely thick as seen by the electron beam. So if the sample deviates from these requirements, the quant results will be off. This is the basic assumptions of any CAF or any SEM-based quantification technique. For TEM quantification, it is slightly different. So how much trust can we put in these quantification numbers? We can use two metrics to break it down. The precision, or how repeatable are the results if we run multiple measurements, and the accuracy, how close are the results to the true composition of the sample. The precision we can calculate or just do numerous measurements and see what the variation is. The accuracy, in this case, the example we'll be showing, you know what the sample is, so we can tell the accuracy, but most of the time you will be working with an unknown. In this case, you can't know the accuracy. If you already know the composition of the sample, there's not much point in collecting spectra from it. We'll be working with the sample we showed before, quartz silicon dioxide, and that means the composition is supposed to be 46.74 weight percent for silicon and 53.26 for oxygen, or 33 atomic percent silicon, 66 atomic percent oxygen. The data I show here is fake data. It's just I applied a random variable and introduced some deviations just to show the function of precision and accuracy. So here we have some relatively noisy data, and I reduce the noise, and we can see we get closer and closer to the true values. The red line and the black line are the values for oxygen and silicon, respectively. So here we can see we have increasing precision since our spread becomes less, and we can see our standard deviation of the measurements I simulated here is going to lower values. Also, the precision increases slightly, getting closer to the actual number for the silicon dioxide. This increase is just a matter of statistics, though. The mean value from the auto-generated data would be the exact values. So this is just a low statistics that we see this increase. So this illustrates the increase in precision, the repeatability of the results. In this case, we can see our measurements are off relative to the expected values. Even though our standard deviation is less, we have higher precision, we have less accuracy in this one. We're off from the true values. So the precision in the quantification numbers is primarily a function of random or statistical errors, whereas the accuracy is systematic errors. Systematic errors will typically be deviations from the model, if your sample is not flat, if it's not homogeneous, if it's not thick, or if the values that's fed into the model are wrong. If the observation voltage is wrong, if you're applying a sample bias or the sample is charging, the sample is tilted and that value is not transferred into the model, and so on and so forth. Can also be that the model can't compensate for your setup or the sample itself. This is typically seen if you try to use low energy X-ray lines, something like the iron L, where the exact position and width can be dependent on the binding configuration. So, statistics and counts. The detector itself measures X-rays and adds them to the spectrum one at a time. So we can only detect and process one X-ray at a time. If we have low count rate spectra with short acquisition times, that means we'll inherently have very few counts and poor statistics. So this is an example, same sample, but now real data. 15 kilovolts acquisition voltage, carbon-coated quartz, and we have here 2,000 counts total in the spectrum. So we can see we have bins down here in the background where there's 0 counts, and we have relatively noisy peaks for the silicon, oxygen, and the carbon. The longer we acquire or increase our count rates, the better statistics we get in the spectrum. Here we have 4,000 counts, 10,000, 40,000, 150,000, and 665,000 counts. So we can see we get much nicer peaks, much smoother background. But if we go back to the noisy spectrum, 2,000 counts total, I went through and repeated this measurement 15 times and did the quantification, and these are the numbers we get. So the black dots here are the silicon quant numbers, and the red ones are the oxygen quant numbers. We can see we get a mean value for silicon of 45.73, just about 1% off, weight percent, from the expected value. And for oxygen, 54.27. No surprise that one is 1% off again, because these are normalized values. Everything have to add up to 100%. That's one of the basics of standardless quantitative analysis. So we can see we're not too far off from the actual expected value, but we have a lot of spread in here. Our standard deviation is high, so we have decent accuracy but low precision. If we increase the counts, our precision will be better. So if we do the same thing for the 665,000 counts, we can expect better results. The plot I have here, it's not the statistics, it's just single spectra and clicking the quant button and plotting in what did we get from that single spectrum. And with the number of counts in the spectrum increasing along the x-axis. So we can see with few counts, we get a lot of variation in the quant numbers. A few of them hits right on line, but that's purely coincidence. But as we move out, increasing the number of counts, we get closer and closer to the line. And at one point, it's only minor changes that we see in the results as we increase the number of counts. So increasing the number of counts in the spectrum increases the precision of your data. How do we do that? Well, there's two options. Either increase the acquisition time. So here we have 1 million counts total in the spectrum, acquired in 500 seconds, 5 seconds. So this is about 10 minutes acquisition. We can also crank up our beam current and increase the count rate. Here we have 1 million counts again, but only 10 live seconds, so much, much faster. So what's the difference, and what do you gain and lose by the fast spectrum acquisition? Normally, we don't want to sit around, but there are people who claim you do need to go slow in order to get good quality data. So what's the trade-off here? If we want high throughput, we need to use a fast amp time. And that generally means we have a reduction in the quality of the resolution. So our peaks will be wider. So this graph is an illustration for the given detector I used for the data collection here. It's an Octane Elite Super detector. And we can see at the 768 amp time, we start off with a base resolution of around 123 EV. So this is a very good resolution detector. 384, very little change in the detector resolution. As we hit the 192 amp time, we go to maybe 125, followed by the 128-ish, 131, At the 024 amp time, we get up to around 137 EB. So our resolution gets worse as we run faster. But if you look at the top of this plot, we can see the max throughput at that given amp time in 1,000 counts per second. So at the 768 amp time, the highest count rate, or the highest throughput, the highest number of counts I can put into my spectrum is 23,000. Go to the 384 amp time, we go to 46,000, and go to the 024 amp time, we can now maximum put 540,000 counts per second into our spectrum. So the acquisition time will be significantly reduced as we go faster, but we do lose resolution. If we take a look at the spectra here, again the silicon dioxide, I have overlaid for the different amp times I've illustrated here. And if we zoom in on the silicon peak, we can see, yes, the peak does grow wider as expected when we run fast. So here we see the peak broadening due to the faster amp time. But if we collect spectra, 1 million counts roughly, and do the quantification numbers, there's not too much variation in the total quality of the results. Again, this is the same count number in the spectrum, so the precision is expected to be the same, but we have worse and worse resolution as we increase or go to faster amp times. You can see here the 024 does have a slight deviation from the expected values. This is most likely because we also have a trade-off in the low sensitivity or low energy range for the fast amp times. This is a carbon-coated sample. So if our carbon coating correction is not as good as it could be because of a bad carbon peak, then that would give change in results. A steel sample or something like that where we're not interested in carbon would probably not show this reduction. But the important thing to look at here is also the time it will take to acquire the 1 million counts in the spectrum at a 30% dead time. 768, it would take about 60 seconds. Whereas at the 024, it will take just less than 3 seconds. So it's a significant gain in the time it would take to acquire. So acquisition time can be reduced significantly with no or limited loss of the quantification accuracy and precision. So what do you gain and lose by doing this? We talked about the resolution for one. The other thing, well, you gain these, but we're not really happy about them, Pileup peaks. This is what happens when you have two X-rays hitting the detector simultaneously. And when you increase the count rates, this has a higher probability of happening. This is one of the reasons that people generally recommend to do quant at low count rate. But is it a real problem? That depends on how well you can separate them out. Going to higher count rates does increase the probability of pileup, and that's what we see here. The two spectra have the same number of counts in them, but one was acquired at a slow count rate, which means long spectrum acquisition, the other at a high count rate, where we can acquire the spectrum in a short amount of time. On the right-hand side, we show our pileup correction on the fast spectrum, so we can calculate these peaks. So if you're really starting to drive your detector to the fast count rates, it does come down to how well can the pileup correction be applied. And we'll get to the requirements for the pileup in just a second, but in general, this can be done very efficiently. So here I show an aluminum copper sample, aluminum on the left-hand side, copper on the right-hand side. If we click quant on this, I highlighted the aluminum here, it will happily calculate a 59 weight% aluminum in this sample. This is wrong. This breaks one of the first requirements we have for our quant routine. The sample has to be homogeneous. This is not a homogeneous sample, so the results are wrong. This is 100% aluminum and 100% copper. And the quant results will not reflect the relative area coverage either. So this is a bad approach to do. Don't click the quant button if you have an inhomogeneous sample. But on top of that, our pileup calculation also requires an homogeneous sample to work. So if you have an inhomogeneous sample, the pileup correction will not work either. We calculate the probability of two X-rays hitting at the same time. So one of the things we calculate is the probability of an aluminum and copper X-ray hitting at the same time based at the spectrum. That's the small peak you can see at the very right of the spectrum above the copper K line, copper K beta. So we calculate that this will happen, but obviously it will not. There's no location in this sample where you'll have aluminum and copper X-rays being emitted at the same time. We also heavily underestimate the aluminum sun peak, which is right around 3 eV in this spectrum, because there's a much higher probability of two aluminum X-rays hitting at the same time, since there's pure aluminum in this sample. So just like the quant routine, pileup calculations will not work for inhomogeneous samples. In general, we can do very nice pileup correction, but it does need to be a homogeneous sample. And with that, you can do very high count rates and compensate for this without much of an issue. We'll turn over to Tara now, but just before anybody cries foul and says that, well, this is a silicon dioxide, peaks are nicely separated, and resolution doesn't really matter for this, so the data is not valid. That is a very good point, but at the end of this, we will show you a galena sample to address all that. But for now, let's turn over to Tara, and she'll explain a few things that we did to illustrate these points.
Hello. Thank you very much, Jens. It's very nice to be here. I would like to start off with just a little bit of a conversation about why we work in some of the conditions that we do. Things like working at 20 to 40% dead time. And so it's a little bit of a traditional perspective. It is a matter of kind of setting a rule of thumb and working at that set condition over and over again. But I'm going to question that assumption now, and rather than say working at the 20 to 40% dead time, which was the traditional answer, I'm going to say let's explore different data studies that allow us to better understand the process times and the performance, and see how the data may update our approach to dead time. One of the things to think about is early on, the dead times that we would traditionally use would be dependent upon the process time. This is also known as amp time, and so you'll hear me talk about process time and the word amp time. Those are interchangeable values that describe how quickly we process an X-ray count when it hits the detector. And that was one of the questions that we received just a little while ago, so I wanted to make sure that I answered that straight away. In times past, we had much slower process times, and because of the slower process times, we had to choose either, say, a 40 microsecond time constant, or amp time, or an 80 microsecond amp time. And one would allow us to process the counts longer, provide more stable results, which gave us better resolution, say 131 EV. Whereas when we would want to work for maps, we would work at a faster process time, say the 40 microsecond time constant, which would allow higher count rates and increase our productivity. But the compromise was that we would work at resolutions in the range of 160 or 180 EV or even poorer. So we accepted that compromise. It even, in fact, became a rule of thumb. And that rule of thumb is something that I'm questioning now, and I'm going to show some examples of data that will allow us to see why when we work at faster process times, we're able to get quality results quickly. So the data example that we're going to walk through today shows a few different variables that we change to explore the relationship between collection time, collection rate, and speed. And the collection time is how long we collect for in seconds. The collection rate is the counts per second, or how many X-ray counts are hitting the detector. And the speed is the amp time, or time constant, how quickly we process the X-ray counts when it hits the detector. And this study takes a methodical approach, meaning that we're working with a known standard, mineral material with known values, And then we have three different variables that I just described above. But we're going to change each of those variables one by one and explore how it affects the quality of the data that we achieve. So the first part of the study is to change the collection time. And so the question that we often receive is, how long should I collect my data for? And this is a very common question, and it is so easy to answer with an answer that starts with, it depends. And certainly it does depend on a number of things, and that is the conditions that you're working at, namely your beam current or your counts per second, and also your process time. So the dependencies are, can your sample handle the 15 kV? Can it handle the a little bit higher beam current? Right now we're working at a beam current for these conditions about a little bit less than half of a nanoamp of beam current. And for this particular material, we were looking at a trace amount of manganese. And that's because it's a little bit more difficult to look at a sub 1% material. And in this case, what we've done is we've collected the entire spectrum at 10,000 counts per second with a fixed 1 microsecond amp time. And the variable was the collection time. So we collected at 1 second, 10 seconds, 50 seconds, and 100 seconds, an increasing amount of time to look at how it changes the results. And as you can see in the results, the longer that we collect for, we get actual values that are closer to the known value of 0.46 weight percent. And so the first two data points, the 1 second and the 10 seconds, give us a little bit further difference from the known value. And this difference here is the difference between the actual and known value divided by the known value. So how far off we are from the known value. And you can see the first two just don't get us in a good range. But anything above 10 to 50, anything between 10 seconds, somewhere between 10 and 50 seconds, we start seeing that the data aligns more nicely to expected values. And in fact, better than 10% difference from the known value on a trace amount is quite good. So even that 50 seconds collection was quite good. And by the time we get to 100, we're probably not going to get any better than that as far as hitting close to the known value. A few notes here. Carbon coding correction was used in the software. That's because the sample was a mineral sample. It was coated with a thin layer of carbon, about 40 to 50 nanometers, and that allows us to dissipate the charge or get rid of the electron beam charge. But what it also does is absorbs the X-rays on their way exiting the material, and so it has some preferential absorption, particularly for the lower energy elements. And but of course, it affects everything throughout the range of elements. When we use the carbon coding correction factor, it knows the magnitude of absorption for the various elements and corrects the concentrations accordingly. Works quite nicely and was used here to give us the best data and results. And all of the results are reported as standard lists. So we really just clicked a button and we got some quantitative results. The result of this first part of the work was that as collection time increases, as expected, the accuracy does increase. And the word accuracy here is used to describe the difference from the known value. And to illustrate what we're looking at when we're dealing with the different spectra, so the first one that we see here is just the simple 1 second collection time. This is what I would consider a very low collection time for the lower count rate. And at 1 second and 10,000 counts per second, you can see that we have very sparse data. The peak that we're looking at is the iron K alpha peak. Just to the left of it is the area that we would expect to see manganese. And if we're measuring a trace amount of manganese, the 1 second visually confirms that certainly the difference, the greater difference is understandable. But when we now display the 100 seconds collection, we could see that we have a nice clear iron K alpha and K beta peak. And to the left of that large iron peak, we could see that we do have a small amount of the manganese peak present. And certainly that goes in line with the actual quantitative results. So visually, we feel more confident that the manganese is detectable, and quantitatively, the results have greater accuracy compared to known value. So we got good results the first time around, and the first time around we collected for various collection times. Now what we're going to do is look at various collection rates. So we're going to vary the number of counts per second that hit the detector. And the first experiment showed us that for anything above 50 seconds at 10,000 counts per second, we got pretty good data, definitely acceptable data for this trace amount. And so we'll use that 50 seconds times 10,000 counts per second, gives us 500,000 total counts in our spectrum. And I'm going to use the word sum total spectral counts. That's the number of counts per second times the number of collection seconds, and that gives us the total amount of X-rays in our spectrum. And we're going to keep that number fixed now. So we'll keep that total spectral counts fixed and change the way that we collect those sum total counts. And so now we've collected at 50,000 counts per second, and in order to reach 500,000, we only have to collect for 10 seconds. So a whole lot quicker, right? We get to do a lot more data collection in a lot less time. It makes our jobs more productive, and it also makes us a little bit more interactive with the data and the software as we collect it. But the question is, do we lose anything by upping the count rate and decreasing the collection time? Do we have the same quality? And so if we look here at the two different conditions, so what we've done here is then report the mean value. And what we've gotten is good values of 0.43. Coincidentally enough, they both give the same mean value. So you can see that the data difference between the known value of 0.46 is the same. And then what we've done is collected it 10 different times, and we got many sampling data points so that we can look at the standard deviation of those results. And so by doing it 10 different times, we could see just a little bit of variation in the standard deviation. And the 50,000 counts per second gives us maybe a little bit larger dispersion, a little bit larger standard deviation. And a note here is that this is why we're reporting the results in terms of precision, because with standard deviation, we look at the spread of the results, and the precision tells us how close repeated attempts are to each other and to the mean value. Yesterday when Jens and I were preparing for this presentation, we had a really neat conversation about how to actually look at data. And so the way that I just described statistically was a different number of samples, or 10 samples, 10 sampling points, and getting the mean value, and then looking at the standard deviation of each of those points against the known value. But another way of looking at it is each spectrum itself is actually a number of sampling points. And that's because we take a whole spectrum, or a spectrum energy range of counts, and those counts are collected in intervals. So as Jens explained earlier, the concentration formula takes net intensity, and that value is in terms of counts per second. So there are intervals. The longer that you collect for, the larger number of intervals that you have to work with. So even just one spectrum in and of itself gives us the ability to report precision results, because we have many sampling points within that spectrum when we consider it in terms of CPS and integrated intervals. All sorts of fun conversations to have with colleagues. So the final aspect of this study is to look at the process speed and accuracy. And the process speed is also known as the amp time or time constant. And the process speed is really defined as how quickly we process the X-ray counts that are hitting the detector. So from the time the X-ray hits the detector through to when it's registered as a count in the spectrum, then we are able to measure it as a point. In this study, we kept the sum total of counts constant, so we still have that 500,000 total spectral counts again, but we've varied the amp time. And so what we're looking at here in the column to the left is the amp time is speeding up as we go down the list. So the 1.92 is the longest amp time that we're using. The 0.96 was the one that we used in the earlier two examples, and then we've also gone faster. And so these are quite fast processing times. These are current generation electronics, been around for about 5 years or so, but certainly much faster than the old 20 to 40% dead time that we used to suggest. In fact, at any of these amp times, it's pretty hard to get to 20 to 40% dead time unless we're in the hundreds of thousands of counts per second. So now what we're looking at is we know our known value, and we have our actual data in the next column. And the actual data tells us how far off we are against the known value. And you can see in the difference column, as we go from top to bottom, or slowest to fastest process time, there's really not an easily viewable trend. We sort of have a higher number, then a lower number, and higher and lower again. So there's not really any conclusive data that says that we lose quality even when we speed up the amp time. And this is in large part because we have a lot going on in the electronics. Our discriminators are allowing us to keep up with the number of counts that we have and process all the counts efficiently and effectively. Next, when we look at the standard deviation, we see that there's again not much difference between the various amp times. And so the conclusion that we draw here is that we're probably not losing any quality as we speed up the amp time or speed up the process speed. So this is very good as a result to show us that you can work faster, which gives us lower dead time, which then gives you higher productivity, more counts in lesser amount of time. So overall for this study, when we want to draw our conclusions about these three different variables of collection time, counts per second, and amp time, we say, does a longer collection time and more statistics equal better data accuracy? And the answer is yes. I will say that yes, and it's especially for trace elements. In this case, the longer collection time certainly gave us the data quality that we would need and expect for a trace amount, less than 1%. And for us, for this experiment, we were at a sum total of 500,000 counts per second. If you were looking at major or minor elements, I would suggest that anything above 100 to 200,000 sum total spectral counts will probably give you the similar results. Those are recorded on previous webinars that we've reported with some materials with higher concentrations, and we consistently see that this range of sum total counts is going to give you data that has values close to the known values. The other key point is that the better data quality seems to be solely dependent upon the sum total of spectral counts, meaning that it doesn't matter whether you change a higher count rate or a longer collection time or with a lower count rate or a faster process time. So feel free to speed up your count rate, open up your apertures, increase your probe current, make sure your beam is aligned. Anything that gives you higher counts per second will allow you to get the same quality of data but in a quicker time, and then you're able to increase your productivity. So the next example is a previous study, and this was reported last year in a webinar. And it's very consistent to the data that we just saw now, but there are a few notable things because the design was done a little bit differently. And that's where as the count rate was increased. So in the left column you see that we start at about 15,000 counts per second and go up to 200,000 counts per second. The known material has an actual known value of 0.5%, and you can see in the second column under carbon weight percent that we have a series of numbers that are then plotted out in the graph to the right. And the graph to the right has the x-axis showing the count rate increasing as we move to the right, and the known value of 0.5% is up there on the graph. It's not indicated, but you may be able to see the 0.5. And you could see that the actual data that's plotted goes very close to that 0.5%. But what you might also notice is that we have two different areas that we have dips in the data. So the data quality starts to veer away from the known value. And those were also certain points in the method of acquiring the data. And so in order to return the data quality to that same level before the dip, what did we do to process them? And so because I've reported this data before, and I know that we have many people who attend the webinars repeatedly, I'm going to give you all an opportunity to provide some input to see if you can use the information on the previous example to maybe understand what change was made to get the data quality back in line. So as we saw on the previous slide, we were close to the 0.5, and then we started to dip away from the 0.5 known value, but then we got the data back in line. And if you would take a moment to give an answer to what you believe was done to get the data back in line. And I'll give a minute to answer, to think about the question and to answer. And I believe you can change your answer once you've done it. So feel free to change if needed. Make sure you read all the options: faster amp time, lower dead time, higher throughput, or all of the above before you answer. And now I will move along to see the results. And this is great. Most everybody is paying attention. All of the answers are in fact correct, but the all of the above answer is the most complete and comprehensive one. And that is that all of these were done. So the user who, these were our interns last year, they switched to a faster amp time, which then gave them a lower dead time and also provided higher throughput of the X-ray counts per second that were making their way into the spectrum. So all of the above is the best answer, but all of the answers are indeed correct. And certainly the theme of my experiment is to show that lower dead time gives you just as high quality of results, but in quicker time. And so looking at the data again, we could see that switching to the faster amp time lowers the dead time, gives us more throughput, and also falls in line with the study that shows that higher statistics give us more quality of data. So one of the aspects of this work that I wanted to make sure to include, especially after talking about our webinars with a recent attendee, was that we make sure that we remember everybody. There are many industries and applications where high counts per second and or higher beam current or higher kV, where they're simply not possible. You might have a polymer material or a highly charging material. You might have to work at low kV because you're looking at something on the surface. So all many good reasons to work at lower count rates, and we haven't forgotten about you. And so this study shows an example of how you can gain the benefits of the faster process time or the lower dead time, even at low counts per second. So for anybody who has said, well, this study doesn't apply to me, this couple slides may apply to you. This was done at about 4,500 counts per second and about 140 picoamps on the microscope. So pretty low count rate these days. This was on a large area detector, so we're able to get a pretty decent amount. If this was a smaller area detector, we might have had around 2,000 counts per second. So the data shows us that as we speed up the amp time, starting from the slowest of the 768 and then go to our about 1 microsecond amp time and then to half a microsecond amp time, our dead time decreases from 7% down to 1% to about 0.5%. And each of these happen in about halves, so each time we double the process speed, we double the dead time as well. Or if we decrease the process speed, then we decrease the dead time. And you might say, well, 7% is not so bad. We used to work at 20 to 40%, so why not work at 7%? And you'd be very correct. 7% dead time is not so bad, but 0.5% is about 15 times faster. And when you're working at low count rates, really every amount of counts that you can get really helps, especially if you're shooting for something like the 500,000 counts total sum in the spectrum. It might take you a long time to get there, longer time if you have a higher dead time, and the faster process time is going to help you get there more quickly. And of course, there's a trade-off. There's always a trade-off, but in this case, it only costs us a drop of about 8 eV in our spectral resolution. So really not much in terms of trade-off, but we do get a nice 15% increase in the number of counts that are making their way into the spectrum. So we do still reap the benefit of the improved dead time, or we can keep the collection counts fixed and have a shorter collection time. An interesting aspect of this particular work is highlighted by use of a really nice detector, which was the 123 EV resolution detector, which shows something that no other detector, in my experience, typically shows. So really only in the 123 to 125 EV range does this apply. And that's where our low energy performance is so incredibly good that we're able to see some things like peak separation where we don't normally see it. But even in this case, we're able to see such a good high quality peak resolution at the low energy end for this level of detector. And so this was 123 EV on a 60 millimeter detector, which is quite good. And so while the faster process time gives us more throughput and a higher net intensity, it shows some degradation in the low energy. So the visible peak height is actually lower compared to the slower amp time. And so what's going on there is that the slower amp time has such a good resolution that it's keeping all of the available counts into a very narrow range and thereby making the peak appear higher. Now, the net intensity is still actually higher, meaning the throughput for the faster amp time is higher, 1800 versus 1700, so a little bit higher there. But the peak itself is a little bit broader because of the resolution has spread out. Now, as we go higher than the low energy elements, looking at the iron K peak, we're actually able to see that the faster process time does give us a little bit more visible intensity, and you could even see maybe even a little bit more of that trace amount of manganese there as well. An interesting point was that the net intensity, or counts per second, for each individual element varies between 1% and 20% for the different elements. So while we have about 15%, no, I think in this case was 7% more counts. This was the difference between the 768 and the 1 microsecond. So we have about 7% difference in the total counts per second, but for each individual element, we vary between 1% and 20%. And that's because different elements have different excitations, and so we see the gain spread out differently between elements. And now that I've gone through a few different examples with trace amounts and with various collection count rate times and speeds, I'm going to turn it over to Jens for one of the most interesting studies on a very challenging material that has a very common peak overlap. Back over to you, Jens.
Thank you. So what we show here is the spectrum from a galena sample. Galena is lead sulfide, and this is one of the ones that's considered tricky. I have about 125,000 counts in the spectrum total, so decent, but nothing extreme. As I showed in the first few slides, this is around where you can expect good precision, but not perfect. We could increase count rate and get a little bit better, but it's a good starting point. So the problem in the galena sample is this heavy overlap between lead and sulfur. To look at the peak energies, we have the sulfur K alpha and K beta and lead M alpha and beta. These are the primary lines that we see. And between sulfur and lead, we have 30 eV difference for the K lines, and for the alpha lines, and for the beta lines, you only have 22 eV difference. So if I take the peak and overlay it with, on top we have the sulfur overlay, and we can see there's something missing here. There's a low energy tail, and at the bottom I have the sulfur only overlay, lead on top, sulfur on bottom, and we can see there's a slight peak at the high energy range that's missing, and we have a severe misfit from the peak itself. So there is lead and sulfur in the sample, but it is heavily overlapped, which means we have to rely on our model to deconvolute this. Even the best EDS detector resolution will not help you deconvolute this overlap. For something like that, you'd need to go to WDS. So here I have the 096 amp time, where I have 127 eV resolution on the detector, and repeated the measurement for 10 times. And you can see we do have some spread. The precision is not as great as it could be because of the total number of counts, but our mean values are pretty close to the atomic percent ratios. This plot is in atomic percent just because we have 50-50, so it's easier to see. If I now go to our 048 amp time, where I have 131 EV resolution roughly, there's essentially no change in the mean value. There might even be a slight decrease in the standard deviation. This is, I only have 10 samples, so if I had 100 samples, might be a little more clear. This is just a statistical variation. But the point of this is that even with a severe overlap, where most of the time you would tend to go to the slower amp time to get better resolution, even at the high amp time, you can still separate it out, even with the relatively low statistics you have here. But by going to the 048 amp time versus 096, if you collect your spectrum for the same amount of time, you'll now have twice the number of counts in there. Or you can speed up your collection time and get the same data faster. So even with these heavy overlaps, the reduction or the loss of resolution with the modern detectors is not that significant, and you can still do high quality analysis even at the fast amp times. So just a brief summary. The quality of the quantification results is highly dependent on the number of counts in your spectrum. This is pure statistics, no surprise in that regard. But with the modern detector systems, the resolution trade-off by going to a faster amp time is minimal, and often it will have no impact on the quantification results. Easy enough for the silicon dioxide we showed, where there's no overlap, so resolution doesn't matter too much. But even for the galena, where you have severe overlaps, going to the faster amp times does not really reduce the quality of the results. But the faster amp times allows you to collect the high quality data with either shorter acquisition times or much, much better statistics if you keep the time as a constant. Another point is that going to lower dead times will improve the collection efficiency with little to no negative impact on the quantification results. So the rule of thumb of 20 to 30% dead time, it doesn't necessarily apply with the modern systems. If you have 10,000 counts, 20,000 counts on your detector, going to a faster amp time will reduce your dead time below the 20 to 30% and give you higher output counts, more counts going into your spectrum for the same acquisition time. So that means you get higher productivity even at the lower count rates. You can acquire your total number of counts in a shorter amount of time or get better statistics, keeping the time as a constant. And you can do high quality quant even at the faster amp times, even with severe overlaps like the Galena. You don't have to stay at the slow amp times when you have severe overlaps. So with that, I would like to thank you, and we are short on time, but let's just try and see if we can run through a few of the questions while we still have a few minutes. One of the ones I saw is regarding Pileup Peaks. Why is it so bad for aluminum and other light elements and not so bad for the heavier elements? One thing is, where does the Pileup Peak land? If we have aluminum, which is 1.486, the Pileup Peak will be at argon, so right around 3 eV, which shows up right in the middle of the spectrum most of the time. If you look at something like iron, the iron K alpha sum will be out around 13 keV, which is much further out, and the efficiency of the detector essentially drops off when you're out there. So it's further out in the spectrum. It's not as efficiently detected, and that's one of the reasons it seems more severe. Also, the resolution plays a role. The aluminum is a relatively narrow peak, which means the sum peak will also, the counts will be spread out over a small region, whereas the resolution is much broader once you move up in the energy range. So even though the integrated counts can be quite high, the peak will be spread out and the total height of the peak will seem less. And there's also a question about the standard deviation and the error percent that we show in the quant results. The error percent is basically the statistical and model errors at one standard deviation. So it is the expected variation at one standard deviation of the quant results, both the atomic and weight. So you need to multiply the percentage by the atomic and weight to get the expected deviation. That's basically how it's done, but you have to remember this is the model deviation. It doesn't tell you anything about the accuracy. If the model is off, if your sample doesn't meet the requirements of the model, the results can be much further off than the error would indicate. This is pure statistical and error progression through the model. Often you will also see high errors for the light elements because we include any deconvolution and overlap introduced errors. So even if we have a perfect background model, we still include potential errors in the background, and since the background is higher for the light elements, the error numbers are typically higher for the light element range.
I'd like to jump in with just a comment, and the comment is that in the download area, we have a few different pieces of material that you can download. One of them is a quick tutorial on how to do the collection rate and collection time and speed experiment on your own. So if you do want to explore how this particular design works on your samples, then you can download that PDF and try it out on your own samples, on your own microscope, and definitely report the results back into us. We'd love to hear how it works for you on your work, on your samples.
Another question is the flatness of a sample. We require it to be flat. How flat is flat? That heavily depends on what you're trying to do. If you really try to push the limits, there's a paper I like to reference by Nicholas Ritchie and Dale Newberry from NIST called Performing Elemental Microanalysis with High Accuracy and High Precision by Scanning Electron Microscope Silicon Drift Detector Entity Dispersive X-ray Spectrometry. Long title, but the point of it is that they can show there is a difference between a 1 micron diamond polish sample and then repolishing the same sample with 0.1 micron alumina polish. There is a slight change in the precision of the results. But this is when we're really looking at the minute details and trace levels. To do this level of analysis, you really have to optimize things. And most of the time, that's not what we do. Often it's just throwing a sample in there and getting an idea. But if you really want the true good quality results, you do need to polish your sample quite well. That doesn't mean you can't get data out of it, or good data at that, but pushing the limits, it does need to be polished. How about a slant on the surface? It depends. If you feed this slant into our model, in our software we have an option for entering a pre-tilt value, so we know how slanted the model is, or the sample is. We can take that into account in our modeling and still get very good results. We just need to know that the sample is slanted because it changes the takeoff angle and the absorption of the X-rays going into the detector. So a slanted sample or even a tilted sample, not necessarily a problem as long as we know it's tilted or slanted. That goes to the, not the precision, but the accuracy of the model. If the input data to the model is wrong, the quant results will be off, but that can be compensated if it's a known tilt or slant. I see we are 7 minutes over the time, so I think that might be what we have time for with questions. We will get back to you on email with the remainder of the questions. So with that, I would like to thank you for attending. Sarah?
And I'd also like to make sure I take a moment to give a special shout out to Kylie Simpson, our summer intern for the 2nd year in a row. So much of this data was the result of her hard work and also quick understanding of what we needed to get the data. And so we definitely appreciate all of her efforts. Thank you. And thank you to everybody who attended. It is really nice to see so many people coming back in, jumping in our webinar series, and hopefully getting a lot of good practical materials out of their time spent on the webinar. Hopefully everything that can apply to, or at least some things that can apply to your job to help make your lives a little bit easier or more productive, or to also give you materials to pass along to other people that you work with so that they can learn a little bit more about microanalysis. And as always, it's a pleasure working with you, Jens, and Sue as well. Thank you.